Today we're learning about the mole, which means we are going to learn how to count particles. And yes, chemists have their own ways of counting particles. The reason we're doing this is so we can relate mass to chemical amount down the road. Mole is another way of saying chemical amount. And our success criteria is being able to describe the mole. So the mole is not talking about the animal here. What a mole is it's a phrase very similar to a dozen or a pair. We know when someone says 1 dozen, that means 12. If you want to get fancy, a baker's dozen means 13. A pair means 2. These are counting units. They are ways of representing a group of objects as a single unit. So it doesn't matter if you're talking about eggs, if you're talking about apples, feathers, bricks, bowling balls. When you say a dozen, it always means 12. And when you say a mole, it always means a very big number, but it's always the same number. And this is important for chemists because the number of particles in even the smallest sample of chemicals is gigantic. It's billions and billions and billions. It's actually so large that human brains have difficulty conceptualizing it. So instead of trying to imagine a gigantic number that's effectively impossible to count to, we use the mole instead. And the mole is much more countable. This is not dissimilar from the way that we measure distance in astronomy. Within a solar system, when we're trying to measure distance, it's impractical to use centimeters or meters or even kilometers. So instead, we base our measurements off of the distance between the Earth and the Sun. And that way we can compare the distance of planets in our solar system to the Sun based on how far our planet is from the Sun. Because if we tried to explain that number's gigantic, even in kilometers. So it doesn't mean very much. And it's also an easy thing to apply to other solar systems. We do the exact same thing in chemistry. We use a value of a mole as a standard throughout all different chemicals to describe how many particles there are in it. Even though the value of a mole is difficult to conceive, comparing 1 mole to 2 moles is valuable. We could say we have double the number of particles. This definition can be a little confusing, so if it doesn't quite make sense, that's okay. But what a mole is defined as is that 1 mole is exactly 12 grams of the carbon-12 isotope, which is carbon's most common isotope. Now, that means that all of the particles in that sample have to be that carbon-12, and when you get a naturally occurring sample of carbon, they won't be. So the molar mass of carbon is actually 12.01 grams, slightly higher. But the definition is based off of that carbon-12 particle. In practicality, what that also means is that 1 gram of protons has approximately 1 mole of particles in it. And the same thing with neutrons. It's not actually quite that. The numbers are a little bit different, but it's so close you won't be able to notice it. So a mole of protons and a mole of neutrons each has 1 gram of mass. The number that 1 mole represents is gigantic. Way we usually write it to 3 significant digits. So we say it is 6 and 2 hundredths times 10 to the power of 23 particles. And we say that is Avogadro's number because it was named after a chemist named Avogadro, not avocado. So Avogadro's number, that's a huge, huge number. But it's always the same. It's always 6.02 times 10 to the power of 23. Now you can apply that to other things as well. You could have a mole of sand. You could have a mole of feathers. You could even have a mole of moles You wouldn't want a mole of moles because that's enough moles to make your own planet out of moles. But we can use this for more than just particles, but really we just stick to it with it in chemistry because chemistry is the only practical application for it.